In this lecture, we will talk about matrix Lie groups. Lie is the name of the mathematician, Sophus Lie, who studied them. So it's not lie. And let's see, why do we need to talk about this? This is probably a topic that it's first time you're coming across it in this general way. You might ask, well, can we just skip everything and use simple tools? Sure you can. You might be okay for now, but your knowledge will be something like 20 years behind in the current mainstream literature, 20 to 30 years behind. Give it 10 more years and you will be completely irrelevant to the community. So you don't want that. Now, you don't want to be a mathematician here, but you want to know the concepts, why we need them, and why in certain applications they are preferred tools to be used, okay? Some motivations that are more practical, how to learn features that are invariant to image rotations. All of us conceptually can relate to this idea that if we want to classify these cat photos as cat, we will not be probably misled by the orientation of the image, right? It doesn't matter if it's upside down. We still recognize this is a cat photo. Now, what is it that makes it so easy for us to be agnostic to the rotation, 2D rotation of this image? And why it's so difficult for a computer that people need to do? This particular example is related to deep learning and machine learning. They need to do data augmentation, consider all different orientations of the image to expand your data set. And of course, you can't consider all of them because there are infinite possible orientation, just like the circle, right? So you cannot generate infinite examples by just creating different variations of the same data. That sounds very naive and inefficient, and it is. So the modern way to look at this problem is through the lens of symmetry. And it boils down to the fact that you want your features to be equivariant for regression, meaning to have the same orientation as the input, or invariant, meaning to be independent of the orientation of the image. If you can accomplish that, then you have a classifier for yourself that it's agnostic to the orientation of this cat image, right? So it is a very powerful idea, and it boils down to exploiting the symmetry, okay? Now you can think about it in 3D. For point clouds, we like that as well. If we wanted to do place recognition, we probably want to have features that are not widely changing based on what view we are looking at, let's say a shopping mall, right? We want to recognize the place no matter what view we're looking at it. So it might seem to be related to the computer vision or machine learning, but ultimately we need it for robot vision and perception as well. So and it is nice that all of them, they get tied together within this concept of exploiting symmetry. Now, for something like this that is continuous symmetry, you can rotate the image continuously as small as you want, right, around a circle. We need a mathematical framework that describes that efficiently as well. And that's the topic of Lie groups. Lie groups, again, are the best tools we have for studying continuous symmetries of different spaces. Here, it's a 2D space. In 3D, it's a 3D space. Another example that we will deal with it in robot state estimation in this course is how to model a rigid motion of an object or articulated robot. We covered this a little in rigid body lecture. So Lie groups, matrix Lie groups in particular, are the bigger umbrella of that rigid body basically lecture that we covered. This is a superset of that topic. But we are particularly interested in rotation and translation, rigid body motion. What about 3D reconstruction using a monocular camera? In computer vision and graphics, you have a monocular camera. What's the problem with a monocular camera? No depth, right? You have a camera and then no depth. You can take as many images as you want. You will never observe the depth. So what's the consequence of that for something like structure from motion, which is a related topic to SLAM? You want to reconstruct this scene using a series of images. Well, if you don't have the depth, you won't have the scale. Now, is the scale a constant? Is that the case that you can just model the whole scene and then multiply it by some number? That would be still nice. It turns out that's not the case. The scale is a parameter that will vary for every time you're solving the problem to reconstruct the scene. So there is a bigger Lie group than rigid body, which has one additional dimension that has the scaling. That's called similarity transformations. In computer vision, that is used for monocular vision. That's also a Lie group. So it does not preserve the distance between 2 points because the ambiguity in the depth, it will rescale the scene each time. Eventually, you won't have the actual scale, but at least relative to each other, the scene is reconstructed correctly. That's important. What about IMU? Every phone we buy, every laptop, maybe not laptop yet, every tablet, every robot comes with an IMU. An IMU refers to inertial measurement unit. It's a sensor that combines a gyroscope and an accelerometer. Usually also comes with a magnetometer. But the minimal setup is having a gyroscope and an accelerometer. How do you model an IMU? How do you integrate it? Which you might be surprised, but the question that for 30 plus years people are basically studying boils down to how do you model and integrate IMU sensor correctly? If you can only do that, you solve the dead reckoning problem. And that's what you will see in the invariant EKF lecture. So it is just basically correct way of integrating. And by correct, we mean understanding the space that these natural quantities that we measure, like angular velocity and linear velocity and acceleration, are basically living there, and then modeling them as similar as we can to the way they behave in nature. Okay? It won't be perfect, but we can capture the underlying principle in an ideal or deterministic setup at least. Okay? That's a prerequisite for having a model that performs better. We still have to deal with uncertainty. So all of these will make the study of Lie groups a very compelling area. Now, the topic itself is vast. It's basically an area of research in mathematics and physics as well. We want to cover the part of it that we care about. So we talk about matrix groups, Lie groups. First, let's review what is a group. We mean group as a technical term in the mathematical sense. So when we say group, we're referring to a group of objects, a set, that satisfies certain properties. One of them is closure. A group consists of some elements, let's say G and H, whatever they are, and a binary operation. Let's use dot. You can use any, I don't know, any symbol that you like, right? It doesn't matter. If you're a computer programmer, you're used to this idea. I have an operator, I'll just define it. Like you can define the product to be your plus, right, in a computer. That's not a problem. So you have an operator that it's binary because it takes two group elements and it will do something. Now, whatever you do, the results must belong to the group again. You cannot go outside using that operation. That's the closure property. You might guess why we don't add rotation matrix now, because it's a group, you want to stay there. If you add them, you'll end up outside of the group. So we must multiply them. So you can come from this more abstract algebraic construct, then you have to follow these rules. It might not help your imagination to visualize, but abstract algebraic structure will give us a set of rules that we can just follow and things will work out. The second one is associativity. That means the order is not important in the sense that not shifting them to left and right necessarily, but if you multiply G by H and then by L, it's the same thing as first calculating H times L and then from the same direction, which is right here, for H times L, multiplying them by G from the right side. Every group comes with an identity element. An identity element is an element of the group such that you can multiply it from each side and it will not change the result. It will reproduce the same element. The last one, the inverse, every group must have an inverse. And the definition of the inverse is that whether you multiply from left or right, it will give you the identity element. Now, you are familiar with these constructs. Let's verify these two groups. The group of real numbers with the operation to be the addition.
Confused about your definition of identity, because in linear algebra, for example, we say that identity is an element where if you multiply it by another element, you get that second element back. Whereas this equality looks like commutativity.
Yeah, it's the same thing. You get E times G. Maybe I should have. You get your element back, right? It's a mapping from each element to itself. It won't change the solution.
Is it equaling G a requirement for it being fulfilling the identity property?
Yes.
Or is it just some element such that commutativity applies to that element?
As far as we're concerned, yes. I actually can't think of an example if that's the case. But what we mean is that it must reproduce the same result. Especially if we talk about matrix Lie groups, ends up being identity matrix times some matrix A, right? It must give you the same element.
What's the difference between the group and the field or the other thing?
What's the difference between a group and field? That's a very good question. We don't wish to talk about it here. But field a little more sophisticated. You can have scalar multiplication, addition, right? Vector spaces are fields. Now, I know you're curious. We don't want to go that way. That's like off-road. So the best way is to learn what we need for what to do and then grow it from there if you're interested, right? Well, let's quickly verify. If A and B are real numbers, right? We already know that a plus b is also a real number. We know a times b is also a real number, just to verify both groups. So there is a closure. Like 2 plus 3, 2 times 3. We also know that a plus b plus c is the same thing as a plus b plus c. Same holds for the other group. The identity element of real numbers with the addition is 0. So a plus 0 is the same thing as 0 plus a, right? Which is, of course, a. For the multiplicative group is 1 times a equals a times 1. Now, the example might seem trivial, but it is really the same concept we're going to apply to matrices. Instead of 1, we're working with arrays. It's an identity matrix, right? This association hopefully will help you to remove some of the uncertainties that you might face when you see matrix version of some of the identities. What about the inverse element? For the additive group, we have the negative sign, right? Which will give you, of course, the identity element. For the multiplicative group, we have the reciprocal of the element, which will give you the identity element, right? Now, back to your question on field. You combine both of these, you will get a field. You can do both of them, right? But these concepts are abstract, and you can generalize it to many different types of operations and objects. We care about real numbers, matrices, and that will give us already a lot to work with. So when we say group, we are going to assume we have these properties, and we're not going to violate them, right? That's important. Now we can talk about a matrix group. So when I say matrix group now, you can think about these properties. So the matrix group will have those 4 properties. On top of that, it's a group that its elements are matrices. They're not real numbers. In addition to having matrices in a group, we also mean these matrices are invertible. So when we say matrix group, these are matrices that are invertible. Okay? Now, the inverse of a matrix is only defined for a square matrix. So by definition, it ends up being a group of matrices that are, let's say, for Rn, right? N-dimensional group is going to be an n by n matrix that is invertible. Its determinant is not 0. But in general, all the matrices you can imagine we could work with are, let's say, m by n. These are rectangular matrices, right? We're not going to work with all of them. We just work with the square ones that are invertible. That's our setup. This group has a name. It's called general linear groups. This is the biggest group you can get for matrix groups. This is the biggest one. All square matrices that are invertible. So M is a set of matrices that are real number. For example, 1, 2, 3, 4 belongs to M2 here. This is a 2 by 2 matrix. This real means that each of the entries belong to the field of real numbers. Could we drop this? Yes, we could. Why do people write it? Because we could have matrices over complex numbers too. Each entry of the matrix could be a complex number. We won't work with complex numbers here, but those are very important as well. And we can use it in robotics too, but I think it's easier to work with real numbers. In physics, that's very common. In quantum mechanics and physics, orthogonal groups, it's over complex numbers. They use complex numbers. You could make it even more complicated. Each entry could come from the field of quaternions. Each of these numbers could be a quaternion itself. That's also possible. We keep everything as nice as possible, real numbers. So let's add more structure. So last time we start from a bottom-up approach that we talked about coordinates, we talked about deriving 2D rotation, 3D rotation, and then looking into the properties of them because it was a direct cosine matrix. We said these are orthogonal, the determinant is 1, it shouldn't change the volume, and all of that. Now this is the top-down approach. We talked about the biggest possible matrix group we could have. Let's add more structure and then make it more special. So the first one is the group of affine transformations. You already know an affine transformation takes a vector, applies a linear map, plus a translation. And the trick we learned last time is that if we form our matrices into this form, the linear part, the translation, add a row of zeros, as many as you need, depending on the number of columns of A, and then add a single one for your translation. This is called a group of n-dimensional affine transformations. Now, for every vector in Rn, if we append the vector with 1, we can get the action of the affine group on Rn. So this is technically when a matrix is multiplied by a vector, that's the action of that group on that vector space. This is the group. This is the vector space, which is our usual Euclidean space. This is the action, okay? We use left action. Matrix is multiplied from left to the vector. You could talk about right action too.
Why would we want to define it such that once you take the product, that the second row is 1 instead of 0?
Why? The question is, why do we want to construct this matrix such that we have 0 and 1 here?
Right, or like, because you can rewrite your matrix, you can rewrite it such that you end up just x plus t, which is...
Can we? So what is the alternative idea?
Well, if you just had one column.
Tell me, I'll write it. Like, we're open to alternative ideas. As long as it works, it's okay.
Well, if you just had the first row, you had AT.
AT.
Right, and then the thing you're multiplying it by is x1.
Still multiplying by x1.
Right.
This is, let me write it like this. So the question is, we can write this A and T. This is n by n by 1, n by n plus 1, right? So the multiplication makes sense, right? Can I invert this?
No, I suppose.
Well, you violated the condition that we had a group of matrices, we needed inverse element. Yeah, so you got disqualified already. So you cannot break those rules. That's why we set some ground rules, and you can't break them. You have to follow them. Now, calculation-wise, this is not wrong. Maybe in your code you're doing this because you know we will get the same answer, right? And that's not a problem, but structurally, you can prescribe this as a general way of dealing with this group, right? So we cannot talk about the inverse of a rectangular matrix. And that will be a problem. So those 0 and 1s, we're just filling the gaps. So it makes sense and satisfies those conditions, right? Either way, you get the same results when you multiply them. So the affine group is very general, right? It includes scaling, rotation, translation, shear, any sort of distortions you might have with that shear. You could think about translation as a matrix group too. This is so general that covers also, if you talk about Rn and addition, right? We could talk about a vector space of Rn, Euclidean space, and form a group using addition. We could use a matrix group, in particular the affine group, and just set the linear transformation as the identity always. All you're doing, you're just translating. So it is covering that case as well. So it generalizes that to a much bigger class of transformations, okay? So this is the group of translations. And in particular, it's very nice in robot kinematics because we can always multiply matrices, whether we're translating or rotating. And that makes it very convenient, for example, to model forward kinematics or inverse kinematics. All right, so we have the affine transformation. Let's go back to the general linear group, construct another group. Suppose we form a set, which ends up being a group, that all the matrices are part of the general linear group. That means they're square and invertible. But also, they satisfy this constraint. This was the constraint for a rotation matrix, right? An orthogonal matrix. An orthogonal matrix, its inverse is its transpose. Because when you multiply two matrices, you're really taking the dot product of each row with the columns of the second matrix. And when these dot products will give you 0, 1, if they're corresponding, let's say row and column, and 0, that means the columns basically, or rows, are perpendicular to each other, orthogonal. On top of that, when you get 1, that means they're normalized, so it's orthonormal. So this condition will give us the orthogonal group. These are rotations and reflections. Because the only way you can apply a linear transformation to an object without scaling it or distorting the object and preserving the distance between 2 points, what are they? You can rotate it, you can reflect it through an axis you get. Do you have other ideas how you can do that? Let us know if you come up with Anything?
I have a question. For the orthogonal group, should A transpose A also equal to identity?
Yes, because A transpose is the inverse of the matrix. This is a property of orthogonal groups, orthogonal matrices that you might have seen it in linear algebra, QR factorization, for example, or Gram-Schmidt process. You can get a set of linearly independent vectors and create an orthonormal matrix. Okay? Then you get this property. This is more special. It's a square. So it works both ways. You can talk about A transpose, A. Either way, you get identity matrix of size n. Whereas if Q is in QR, if it's a rectangular matrix, you write it from one particular direction. That makes sense. So this is the same orthogonal matrix that you might have seen in linear algebra. So I'm going to drop the matrix multiplication as the group operation, so you can just write your matrices next to each other. It is understood that this is a matrix multiplication.
I have a question for the closure. Only the multiplication operation is in the definition.
Yes, you cannot add A plus B if you have A and B. Both of them are part of this orthogonal group.
As well as for affine matrix and translation.
Okay, the question is, in the affine, we have the addition. My answer is we do not. We did a trick so that when you multiply matrices, we can do addition, translation. You still need to multiply these matrices, right? Because let's say this matrix B, right? You're just multiplying B by this vector Y. There is no addition. Of course, inside the matrix multiplication, you have addition, but that's just the rule for matrix multiplication. That's our group operation. We're allowed to do that. So the maybe unusual path is that when we start from algebraic construct, the rules are very rigid. You cannot break them. Whereas the bottom up was more intuitive. Then you start asking these questions. Can I add them? What will happen, right? Then you have to show case by case that, well, is it allowed to do that or it's not? Whereas this way that is top down, the rules are very rigid. You cannot just break them. I know it might not be satisfying, but it works well calculation-wise. But we're trying to cover both sides as much as we can. All right, one observation here is that the orthogonal group is giving us A transpose equals the identity matrix. Take the determinant of the both sides of this equality, and what we get the determinant A squared equals 1. Okay? Transposing a matrix, it does not change its transpose, its determinant. So we have two options. Take the square root. You can either have +1 or -1. So we end up with two set of matrices. Those who have two set of orthogonal matrices. These are all orthogonal matrices, but there's a group of them, they have their determinant to be +1. There's another group, the determinant is -1. Now, they cannot be combined because these are separate groups. They have nothing in intersection. So we learned that this orthogonal group is a disjoint union of these transformations. Now, we know physically that these are rotations and these are reflections. Using that somewhat advanced justification that the determinant is the volume of the subspace spanned by the columns of our transformation, and the negative signs will mirror the volume. That is interesting. The group is not connected. There still is a group, but it has two basically subsets that are independent of each other. So that intersection is the empty set, and this is precisely what constitutes reflections and rotation matrices. These are two sets of transformations. Of particular interest is a spatial orthogonal group. Whenever you see a spatial, usually when we say the determinant is +1, right? So in this language of matrix group, when you see S, that means we're talking about matrices that have transformation of 1. We're not talking about it as another group, a spatial linear group. These are also matrices that they have determinant 1. Take the general linear group, right? Separate the ones that they have determinant of 1, you get a spatial linear group. This group covers the space-time transformation in physics. You can have 4-dimensional space. You have time-like vector of, this is velocity of light. You have time, you have x. This is a 4-dimensional space. Then using a spatial linear group in physics, they model the space-time transformations, meaning objects that move faster, closer to the speed of light, they experience some sort of deformation, right? If they move slower, and all of that is relative in spatial relativity, unrelated to this topic. But anyway, they use this group in physics. You will be surprised that I actually read some work on the visual cortex modeling, and if you replace the speed of, and what was the outcome is if you replace the speed of light with the maximum capacity that your perception system can handle, then you can actually model space-time version of whatever we do with these transformations. Because, for example, if a car is moving too fast, you're just not going to be able to perceive that. It's just too fast for your eyes. For your visual cortex, that's the basically equivalent of the speed of light. Of course, objects don't move with the speed of light here. But when you lay out that setup, then you can have spatiotemporal modeling in your vision systems, and that's very interesting. So the temporal aspects of it is a convolution across time. It causes motion blur in images, for example. The spatial version of it is basically whatever you move in 3D space. And both of them happen in images. Okay? So that's a pretty cool topic in 3D computer vision. I do not think it's covered like that, but it would be cool to talk about it like that. We are going to talk about SON. Now, why do we need to talk about SON? Okay, we're back to rigid body motion. One particular reason to study these groups is that we want to talk about the isometries of each space. Now, what is an isometry? An isometry is a bijection, is a transformation that is one-to-one and onto, and it preserves some distance. You can think about just usual Euclidean distance. You have 2 points. This transformation takes these points and transforms them into some other points in the space. But when you take the distance of these 2 transform points, it's the same distance we had before the transformation. This is called an isometry. F is an isometry here. Now, going with the notion of the Euclidean distance for rigid bodies, this sounds like our definition of rigid body. We defined it in a more physical way. My rigid body is a set of particles, their distance. The distance between any 2 particles must remain fixed as I move in the space. So when you hear isometry, it's talking about the same topic. Now, if it's a linear isometry, we know that linear transformation fixes the origin. However, you can have translation as well, then it's not linear. We know very well that translation, right? Will not change the distance between 2 points. If I translate 2 points to another location in the space, the distance is the same. So translation, we saw it last time that it's not a linear transformation, but it is an isometry. So rotation and translation together, they form direct isometries. Reflections are called indirect isometries, or proper isometries, improper isometries. These are all the names you read in the literature. Now, what is SON physically? I know it's hard to visualize these sets when you talk about algebraic sets, although algebra makes calculation easier. But for a particular case of SON, it's not very difficult to imagine. So a special orthogonal group of dimension n is a simultaneous rotation of n perpendicular planes. In 3D, you have 3 planes, just like here. Each plane is defined by a normal. When you rotate these 3 planes simultaneously at the same time, this motion is described by SO3. But whatever we talked about is general for any dimension. Of course, we're most interested in 3D. What about SO4? Help me visualize it. So for SO3, we know that we can rotate in 3 independent ways, which is take every, I'm going to call this E1, E2, E3, right? So take any 2 unit vectors. It will form a plane for you, right? And then you can rotate using the other vector, which is normal to that plane. So we have 3 ways to rotate. You can do a quick check because the first time I want to rotate, I have 3 options to choose from these bases. The next one to complement it, right? And form the plane, I have 2 options because one of them is chosen already. And the last time, I have 1 option. However, the order I choose these vectors is redundant because if I choose first and second, it's the same as second and first. So divided by 2, you get 3 ways to rotate. For S of 4, you have 4 times 3 times 2 times 1. That's a lot of way to rotate. Is this correct? 12, 24. Is this correct? It is not. We'll see why.
Why we divide it by 2?
I made it up. You believed me. There are 6 ways to rotate in SO4.
So I was wondering, so when you say simultaneous rotation, is it, are you, I'm just trying to understand, are you saying that this is different from, like the traditional way of rotating, which is that first you rotate around like E1 and then you rotate around E2? Let's say.
That's a very good question. So when I say simultaneous rotation, do I mean independently about each of one? No, I mean simultaneously. Think about all 3 planes together and all the different ways you can rotate them. That is the fundamental difference with thinking about them as independent way of rotating about, let's say, E1, E2, E3. Thinking about them as decoupled rotations will cause a problem, which we will see more about it as we explore more in the invariant cave lecture.
So it's different from Euler angle?
It is different from Euler angle, right? So the motivating example for the invariant state estimation is that choose Euler angles, derive the aerodynamics, linearize, see what you get. Then use this method, derive the dynamics, aerodynamics, linearize, you'll get a matrix that is constant. So it's completely different. So there is a fundamental difference when we do the calculations that will be convincing enough to use them. Conceptually, I think you pointed out a very good difference that you need to think about them simultaneously. And when you start working with Lie algebras, each of them will give you a basis, and we combine them before turning them into a rotation matrix. Whereas when you use Euler angles, you turn each of them independently to a rotation matrix and then combine them, right? That's not a good way to do it.
So we define SO and ON plus. This implies that each rotation in SO3 is the same direction.
I don't think I understood the question. You mean?
So why we define SO and is equal to ON plus? Is that the orthogonal?
Oh, your question is why did we define a special orthogonal group to be this ON plus? Why not? I mean, you could use this name, then I would choose a different name. That's okay.
Why is
Okay, so what's the meaning behind this plus that makes it important? Because these are rotation matrices, as we derived last time. These are orthogonal matrices that acts as linear transformation that will not change the distance between any 2 points on a rigid body. When applied to your coordinate frame in the appropriate dimension that they are meant to act on, right? SO3 acts on 3D vectors. SON acts on n vectors. What they do, they rotate your frame all together. X, Y, Z axis together, right? Not separately. They will remain orthogonal and normalized, okay? This is the property of this subset, which has the determinant of 1. It is only sufficient to build one example, use the one that has determinant of -1, and see what happens, right? You will see immediately that it will not satisfy this property because it will mirror it. And we know we don't want that, right? We already know that we don't want to mirror. We want to continuously rotate our objects. That's how sensors move in the space. I hope that's convincing. Numerical examples can help to see the differences. And I will give you some of that maybe on Piazza on notes and in homework. So the name is convention, but the reason was what we talked about. Talked about isometries. So important group that captures the isometry of the Euclidean space is the special Euclidean group. Now you know that if you drop S, this is a Euclidean group that probably this is just any transformation. So it's not rotation. What should it be? Or we could say general linear. Or it could be other groups too, right? So special Euclidean group, A is definitely a rotation matrix. T is just a usual translation. And our rotations are based on the right-hand rule. We don't work with left-hand convention, right? Your right-hand thumb along the axis of the rotation, bend your fingers, that's the positive direction of rotation. So we are back to the group of rigid body transformations. So how many of you are members of this important society? There's a lot of material and discussions online. I encourage you to read some of them. Okay, I see some hands. That's what people see in the recorded lecture. So really? In Michigan? They have members. If you see this at home, I made that up. See, people usually say in lectures, you can always say it, even if you don't see any hands. Because you don't know what I'm seeing behind you. So this is, now if you're not a member, you should be very excited about this next topic. So you can't complain. Now we're talking about curved spaces, and just a little bit, not too much, because then it will become a differential geometry course. It will be off topic again. So a manifold is any curved shape, surface, such as this circle, that we can chop it up into pieces, and we can flatten each piece. In other words, locally, you can treat this as a Euclidean space. Here, a real line, right? You can chop the circle, flatten it, and then think about it as just real line. And in particular, for circles, we do that all the time. We just treat angles as just a real number. Maybe we just wrap sometimes to make sure it's within minus pi and pi. So for us, this is the manifold. No sharp edges, everything is smooth and nice. No square, right? So it's called a smooth manifold. Why this is important? Well, because all the calculus we have, it's for Euclidean space. If you can look at a surface, it's just a surface in 3D space that you can visualize. If you look at it locally and you describe it to be flat for maybe a small region, then we can apply our calculus to that area. And then maybe we move from here to this area, and then you switch to maybe a different neighborhood. So you might need to talk about different coordinates for each region. It might not be the same, but they must agree on the overlapping part and smoothly varying, right? So these are called coordinate charts. And Euler angles are one type of charts. So they don't cover the whole space, just part of it. In particular, that singularity that pops up is the part that is missed. No matter what configuration of Euler angles you choose, you miss that singularity. With different charts, the singularity might move to different value for your rolled PGR, but nevertheless, it's there. So this is a manifold. You're familiar with sphere, maybe, right? The surface of a planet. If you ignore all the mountains and oceans, just think about it as a sphere. This is a manifold. The Euclidean space itself is a manifold. It's a flat space, R3. This shape is called torus. You have one circle like this, and then you have a second circle like this. So move that circle around the other circle, you get a shape that's called torus. That's also a manifold. So mathematicians are crazy about doing calculation and these spaces because they find flat spaces boring. We don't. We like them a lot because we can make money from flat spaces. So we want to make sure things remain as flat as possible. We can do usual calculations. To do that, we need to talk about a tangent space. To understand the geometry of a surface, which is the topic of Riemannian geometry, we need to talk about tangent space and tangent vectors. Imagine this is a surface. You can think about this as R3. So the entire R3 is your ambient space, just like this classroom. Then there is this surface, somewhere floating. Clearly, this is not the entire space. The ambient space is so much larger. This is just a piece of the space. It is a subset of this classroom. If it's curved, which I can't bend it so much, then you can talk about a particular point on this surface. Because it is curved, if you consider any smooth trajectory that is living on this surface, right? It's like a pattern tattooed on your arm, right? It doesn't live in the ambient space. It is living on that surface, this trajectory, okay? It cannot come off because that's where it lives. At a particular point, we can talk about maybe a tangent vector. If you parameterize the curve, and you can talk about derivative, maybe you can talk about velocity. But anyway, you can just attach a bunch of vectors like this. How many of them you can attach? Different magnitudes, different directions. In this particular case, how many? 2? I just did 1, 2, 3, 4, 5, 6. Have some faith in my drawings. Okay. Usually there's usually 1 or infinite in math. If it's not unique, then you can go as high as you want. So infinite. This is in particular. This is just the R2 plane, right? You can think about it as a R2 plane attached to this point. So all the possible tangent vectors, velocity vectors, are in this plane. Different directions, different magnitude. So collect all of these vectors, which is R2 here, name that to be the tangent space at a particular point x. So M is my manifold, this surface. T means it's tangent. X is at what point? Now, for the Euclidean space, when you talk about the tangent space at a particular point, it's the same thing everywhere because it's flat. But for surfaces, it matters where. If you choose a different point, then you have to talk about where you are in that space. That matters.
You said that you're able to draw as many vectors as you like, but it seems like you need more than one gamma curve to define a plane. Because when you take the derivative of gamma, you get one vector. And so it seems like you need another path along that surface to define a second vector to make a plane.
Okay, so your question is that just knowing that I can have a point and a tangent vector is enough to talk about this tangent space.
I'm saying that just having one point and one derivative vector seems like not enough because you could rotate that plane about that vector.
Can I talk about a tangent vector to the circle at this point? You can have
Because your ambient space is in R2.
You can have any, well, in this case, the tangent space is the real line, right? My vectors can have positive and negative directions and different magnitudes. They are orthogonal to the center, but that's not important. That's what defines the tangent, right? In this case, also, we know it's tangent. That means what it means. You can parameterize the surface, you can talk about the tangent vector, right? Or you can see it in the ambient space and talk about the gradient that will be the normal vector. That will give you the tangent plane to a surface, right? From multivariate calculus, we know we can calculate that. Then you will have a plane that is tangent to the surface at that particular point.
If you only have a single path and you compute a single derivative vector, wouldn't you also have a plane that's rotated about that vector, a different plane?
So let me see if I understand. You're saying that if I just have this path, will that generate this tangent space at a particular point?
I'm saying that it won't unless you have two paths.
I think the tangent space is for a point, not a single curve.
I see. So I'm saying that you need two vectors to make a plane, right? You can't define a plane with one vector.
Yes. Was his answer good? I want to make sure it was recorded. What did you say?
I think if you have a point, then you can have structure thing.
Yeah. So if we have a point and a vector, can we? We need two vectors to construct a normal. That's your point. But I'm saying that all of these tangent vectors, so I have more than two.
Yes. You have, well, if you draw more paths, you can have more paths.
No, for the same path, I can have different velocities at that point. One time you're going with 1 meter per second, next time you're going 2 meters per second at a different direction. That's already two vectors, right? But my options are unlimited. So, and we need that because the object that is moving, the camera, can rotate in around about 3 axes and can move in 3 different directions with any velocity, virtually any velocity at any point in time. So the tangent space in one point considers all such velocities. But the point of this figure, so does that answer your concern that how to construct this tangent space, which is not something we're trying to do here?
Yeah.
The shape is just saying that there is a tangent space, all these vectors are living it, that constructs the tangent space. Later, for a particular group, we want to construct that.
Yeah, that's good enough for now.
Okay. So that's one of the tricky topics based on experience, tangent space. But if you limit yourself to surfaces in 3D space, it works just fine. That's exactly what it means. Now, the dimension of a manifold is the dimension of its tangent space. We have 2 examples here. In particular, the dimension of the tangent space of this surface is 2. You can also relate to this idea that you need 2 parameters, maybe, let's say, x1 and x2, to be somewhere on this curved space. These 2 points are not the same as ambient space because this point in R3 obviously have x1, x2, x3. I'm going to use different numbers, symbols. It is somewhere in that ambient space, but on the surface, you can parameterize it with 2 numbers. This dimension is captured nicely by the tangent space, which is 2. For circle, it's 1. If you know the angle, you know where you are in the circle. So the dimension of this manifold is 1, even though it's embedded into R2 plane. So the ambient space here is R2, right? So this concept is, why do we need this? Now, we need this because we talked about from a somewhat dry algebraic path about matrices. But when we reach to the topic of Lie algebra, we need this geometric intuition to talk about, to define the Lie algebra. You have a question?
Yeah, I was wondering, is your manifold dimension always going to be 1 less than your space dimension, or are there exceptions?
I don't think so. We did not write it that way. Otherwise, I would write it's always 1 less than, you mean the ambient space?
Yeah. Like, what kind of break?
No, because you can embed the circle in the 3D space too.
Okay.
You can have, I mean, these are things that you read in math books, right? Engineers don't fool around with these examples, but you can embed the circle in just a 3D space. Now the ambient space is R3. The circle is the same still. It's 1-dimensional. So no, the concise definition is talking about the tangent space because you want it to be always true, right? But it's a good example. Back to matrices. Now, algebraic objects will not necessarily give you geometry. We're going to claim that matrices are geometric objects as well, matrix groups. Because if you have a 2 by 2 matrix of real numbers, you can easily arrange them in a 4-vector, right? And then you can work in a 4-dimensional space. Now, you might not do this operation, or for whatever reason you're comfortable to work with this 2 by 2 arrangement, but there's a clear, it's called isomorphism. You can go back and forth without losing anything. So you can think about your 2 by 2 matrix as R4. Now, your matrix has some constraints. It's not all of them. Maybe you're working with orthogonal groups, right? So it's not going to be the entire, let's say, R4. It's more like this surface. So your matrix group, we do not know the shape of all of them. For some of them, it's easy to guess or talk about them, but not necessarily for all of them. It's more like this. Because the constraint in the definition of the matrix group will form a subset of that ambient space. Because otherwise, it would end up being just the Euclidean space, not the matrix group. Okay? In particular, I'm talking about this A transpose A equals the identity. How can you have a 3 by 3 matrix, 9 numbers, flatten your matrix and call it a 9-dimensional space by ignoring these constraints? If you only go after those 9 vectors that also satisfy this constraint when you arrange them into a matrix, you clearly need to pick a subset of those 9 vectors. So in that sense, we can convince ourselves that matrices are geometric objects because they are a subset of some Euclidean space. Now, you can also prove that they are very nice objects because of this multiplication, invertibility. All the operations are smooth. You won't end up with any singularities in this case of matrix groups. So we do get a smooth manifold. I can give you reference for proof. We are not so much interested in that. But they are nice geometric objects as well. Now, if that's the case, now I can talk about the tangent space of a matrix group. We just defined the tangent space. I'm just using more sophisticated notation here. But all I'm saying is that the tangent space, if I have a subset of a Euclidean space, G, its tangent space at a particular point is the set of all initial velocities, these vectors, we call it V, for a path that goes through that point. It's precisely this shape that I have this manifold, I have a path, this is gamma, this is G. Take a path, this path goes through G. Define a neighborhood here. Within that small neighborhood of that point, I want this path to be smooth, differentiable in the sense that if you have two basically entries to parameterize this curve, I want them to be differentiable in the sense of usual real calculus. You can take derivative, you can work with them without facing any problem. Now, within this interval, this point is my 0, right? I just define it. I parameterize this curve to be like this. When gamma is 0, when gamma evaluated at 0, it goes through that point, G. Then you can talk about its derivative at that point, all the possible velocities you can have. My pen from here is going to this point, right? At the particular point, what are the set of velocities it can have? Whatever it can have, that forms the tangent space at this point. Why we just don't talk about velocities in the Euclidean space? Well, because we want to work with rotation as well. Rotation is not a flat space.
So the tangent space is a set of all the functions of gamma prime?
Gamma prime is the velocity.
So it's a vector.
But at a particular point, because as soon as you move a little bit along the path, you're no longer in that tangent space. That's the reason calculation in curved spaces is challenging. You need the notion of covariant derivative to deal with moving along a curve. I'm talking about the derivative of a function. But for the tangent space, at this particular point, right, you have your plane, all the velocities at that point. Now, we parameterize gamma with t. T varies between just minus epsilon and epsilon, such that when t equals 0, we are at that point, right? This is the same thing that you might have seen in your calculus course when you parameterize a line or surface with a t, right? So that's the general definition of the tangent space. Now we're ready to tell you the truth about Lie algebra. Lie algebra of a matrix group is just the tangent space at the identity. Okay? You might ask why the identity element? There is a very simple reason, because all groups have the identity element. You don't want to go back and then figure out how to change the rules for every group. All groups have the identity element. You see different notations. It doesn't matter. And this Gothic symbol usually is used for Lie algebras. So the tangent space at the identity is a Lie algebra, which is a vector space. Space of all these initial velocities. As we will see, gyroscope will give you angular velocity. That angular velocity is in the Lie algebra of SO3. It is naturally modeled in that space. When you integrate that, you're just basically integrating gyroscope data to track the orientation. It is naturally modeling that for us. So we can talk about the Lie algebra of every particular matrix group. This is the part that we need to practice in your homeworks and Piazza. Of course, I give you the solution, but you want to go through them. For general linear group, it's very easy to prove. And we show that the Lie algebra of the general linear group is basically all the n by n matrices with no constraint. They can be also singular. And the logic is that take a path, that gamma that we talked about, to be identity plus t times A. A is some n by n matrix, possibly singular. Now, clearly, this path goes through the identity, which is what we want, right? We talk about Lie algebra, all the path that we talk about should go through the identity. The derivative of gamma is basically A, right? But also when you evaluate it at 0, it's A. The derivative is with respect to t, which is easy to take. T is just a scalar parameter, like time. Now, the logic is that if you assume this interval is small, then the determinant of gamma at point 0 is 1, because gamma 0 is identity. Okay? As you change t to be a little bigger or smaller within this small interval, the determinant will change smoothly because the determinant is a continuous function. It cannot just change widely. It will change a little by little as you change t a little by little. That shows that if you constrain this interval to be small enough, because the result that we get in gamma defined by identity plus t times a end up being invertible, the determinant is non-zero, therefore gamma is indeed in the general linear group for all t in that interval. Now, if A is the velocity that can be any matrix that is generating this path that belongs to that group, then A must be also in the Lie algebra of general linear group. Okay? So you need to play with these logics a little bit to convince yourself that this is the shape of this Lie algebra. What is interesting about it? Nothing, because all the matrices, even singular. So let's move on from this group. What about SON? Let's define something more familiar, maybe. This is my path. So I know that rotation times rotation transpose must be the identity matrix. If I take the derivative of the rotation matrix with respect to t, and then evaluate it at the identity t equals 0, my path goes through the identity at t0, right? So when I evaluate it, this becomes r dot at 0 plus r dot transpose at 0 equals 0, because the derivative of the other side, the identity matrix, is 0. Now, I can also say that my initial velocity is some matrix A. Whatever, that's the initial condition.
Why we construct the path like this? I plus TA. In the previous slide.
We're talking about previous slide. Let's finish this. I'll talk.
This is different from that.
It is. I'm just assuming there is a path. It goes through the identity with this initial velocity.
Oh, we constructed.
We don't know what's the good path. That's the question. We will be on the quest to find that. It ends up being matrix exponential, but we will talk about it. So therefore, this will give me A plus A transpose equals 0. So I learned that if I differentiate the constraint of the orthogonal group, it will give me another constraint on the velocities, vectors in the tangent space. Now, what are the matrices that when you transpose them, you get the same negative of the same matrix back? Is there a general rule for these matrices? There is. It's symmetric matrices, right? Imagine a symmetric matrix of usual not perfectly aligned, but this is the angular velocity symmetric matrix that we can use. Now, if you transpose this matrix, it is symmetric, so it won't change the off-diagonal terms. Because it is skew-symmetric, the negative signs will also move, so you will get A transpose is negative of A. So we learned that all the matrices in the Lie algebra of SON, or in particular SO3, are skew-symmetric matrices. So we'll just learn the structure of Lie algebra of rotation matrices. Okay? And that's because it's a rotation group, then the velocity is also called angular velocity. You can, of course, write this in a vector too, but the Lie algebra form of it in a matrix spaces is what we see here.
Actually, to go from the first line, RT gamma t to the second, that's
Oh, I differentiated this with respect to t.
Is that RT t given S on like
So,
the term of the RT times R transpose T, and then I'm not sure what comes after that. Is that parentheses?
you're talking about this?
No, mine above that.
Identity. This is the identity matrix.
Oh, I meant the thing before that. Is that? Oh.
Yeah, for the orthogonal, for SON, we had this constraints that RR transpose must be the identity, right? I'm differentiating that constraint, and that will tell me about the structure of its tangent space.
Got it. Okay. Yeah, I was confused. I didn't know those were the equal sign.
Yeah.
I think it's just saying that the equals looks like an S. I think it's supposed to.
Sorry?
And I think you're just saying that the equal sign looks like an S in the second column.
Oh. My bad. No S. There is no S on the slide. There is one here. All right, so now we can go back to that mess that we made for how many ways we can rotate. And it still is good to think about how many ways we can rotate in R4. 6 ways. The dimension of SON is n times n minus 1 divided by 2. Why? The dimension of the manifold or a group is the dimension of its tangent space or Lie algebra. We know the Lie algebra of SON are skew-symmetric matrices of dimension n. These are symmetric matrices with diagonal entries to be zeros, right? An n by n square matrix has an n by n square matrix has n squared entries. All the diagonal terms are zero. It is also symmetric. If you know half of it, you know the other half. So we learned that the dimension of SON is n times n minus 1 times 2. For 3, we get this, which is 3. For 4, we get 6. So in 4-dimensional spaces, you can rotate in 6 ways, which again, you can write down E1, E2, E3, E4. To rotate about an axis, you need a plane, right? You need 2 of these vectors to define that plane. For the first vector, you have 4 options. For the second vector, you have 3 options. You just chose one of them, right?
Oh, that's the reason why you say second.
But then also you can, the order is not important. Because 1 and 3 is the same as 3 and 1. It gives you the same plane. So you can dig into it like this as well. But it's really weird because you have 4 directions, but you can rotate in 6 ways. Imagine a theme park like that. Sounds abstract. Okay, so let's see. What about the tangent space at other points? The identity is nice. It will tell us a lot about our matrix group. But we want to also know what is the tangent space at another point, not the identity. Right? If this is my 0, 0, 0 rotation, what if I'm like this, right? What is the shape of the tangent space at that point? It's a fair question to ask. So the answer is, what makes Lie group nice is that you just need to do a left translation for the vector space as a whole to move it to another point. In other words, the set of all possible velocities won't change. You can still rotate with the same type of velocity you wanted, whether you're here or whether you're at this configuration or at this configuration. So that won't change. And mathematically, that's captured by a left translation, meaning if you rotate your SO3 by R, you get the tangent space of SO3. This is a small SO. So you get the tangent space at R. So as a whole, all possible velocities, you're just rotating the whole space. We're not talking about the individual velocity. That's a whole different story. What is the equivalent of individual particular velocity that we have at this point on a different tangent space? But the space as a whole just needs a rotation. Okay? That's why you might hear that, say, Lie group's tangent spaces are all isomorphic. They're all the same. They look the same. Up to a left translation of the group itself, they're equivalent. And that's very nice and powerful. So if you have your angular velocity A, you use the rotation, right? That's what you do. To know your angular velocity from the sensor frame, right, that you measure with respect to a fixed frame on the robot that you might be tracking, you need that rotation to rotate your vector. That's what we're talking about.
Can you explain again why we know that gamma lies in SON, given this definition of gamma?
This?
Yeah, and then you say that you know that gamma lies in SON. How do we know that?
We don't. We guess. We need to find out. Oh, with the exponential, it is. Then later we should see why. Well, I didn't go through this part. But the question is, to generate this result, we assume the path. And knowing that path lie in the group. Why that's the case? You do need to prove that path lies in the group. Here, I'm giving you an answer. If you take any path like this with the exponential of the matrix, it will. You might wonder why. It's coming up soon, which is now. Next slide. Why? Now, if you know the path, it's the exponential of the matrix. That will tell you that all tangent spaces are the same up to a transformation, left translation, and physically we know that based on our experience working with velocity vectors. We just rotate them when we want to change the frame. Now, what's the best path? Or what is it that qualifies that exponential path? A conceptual way to think about that is like this. If you are at the identity, which I'm showing it here by I, you have one tangent space. Then imagine you're at a different point, this x. We can, of course, talk about the tangent space at the other point. If you take the derivative of any path that goes through x, x dot will be in the tangent space of the group at that point. So it belongs to that tangent space. Now, these are transformations. We know the difference between the identity and x. It's just a transformation by a matrix. If you multiply your vector here by that transformation from left or right, you choose. This must map your vector, right? Translate it to the identity. So you will get another vector at the identity. It won't be the same vector, whatever it is. The velocity, right, of the end effector, when you rotate it with respect to the base frame of your manipulator, it won't be the same. But it is another vector mapped using some rotation. Now, we know that, of course, this is also some other vector C, but not the same as x dot. Because it's in the tangent space of the identity, is of course part of the Lie algebra.
Why is the tangent in the tangent space of M?
Because we just translated by x inverse. X inverse times x gives me the identity, right?
Yes.
Imagine now a vector that is in the tangent space of x. Then this should give me another vector C or A, whatever notation you want to use, that is in the tangent space of the group at the identity. Just like rotating a vector, right? You have a frame, you have a vector v, and then you have a base frame. This is your identity, this is your moving frame. What is the velocity in the inertial frame, identity? And this is, I don't know, you know some rotation and translation with respect to that moving frame. There will be some other vector U. Now, U is rotated version of V. Or depending how you have it, yes, U is the rotated version of V. Depending how you define the rotation, right? Based on the inverse of it or not. I'm talking about the same thing. So x dot equals x times, you see. I might have used, I need to use R inverse here, so this makes sense. Now, this observation is true for all Lie groups because it follows the same rule of vectors and matrix transformations. So we arrive at a fundamental result that for any Lie group, you have a first-order matrix differential equation. If you've had a course in linear differential equations, you can solve this. This is solved using an initial condition. So xt is x0 times, xt is x0 times exponential of t, the velocity. You might have seen it for vectors, it works for matrices as well. So you get a fundamental result that describes the kinematics of all Lie groups. You get a first-order differential equations. We know the solution to the differential equation is using matrix exponential. So that's why it's the most natural path, you might call it best. It's not unique, there are other ways to do it. This is a very natural way to do it for Lie groups. For example, for SE3, the Lie algebra is the skew-symmetric matrix here and a vector V. When you do the left translation, it's just rotating your velocities. Translation will have no effect. We will work with this extensively, if it doesn't make sense now. So that tells us that matrix exponential is the right path because that's the correct way to integrate that differential equation. You can do Euler approximation and other approximation for the solution, but the exponential of a matrix considers all of them. In particular, the series for exponential of a matrix is this infinite sum. In that matrix, it converges for all matrices using, you can find the proof in analysis books using sub-multiplicative norms of matrices. You can prove that this is convergent for all matrices, so there's no challenge for calculations of this. And so for Lie groups, when we talk about an initial velocity that is in the Lie algebra and a path, you will always have this path. From a velocity, whatever it might be, you can generate a path, gamma of t, using this exponential of t times a. So a will change, the path will change. You will get different path. But also you know that if you differentiate the exponential of a matrix, we'll commute with that matrix from left and right. It's easy to prove. I can give you another reason why the exponential is the best way to define the path. Take a skew-symmetric matrix, calculate this term, take the determinant, is not 1. Add the second term, it gets closer to 1. Add the third term, and fourth term, it gets closer. After fourth or fifth, it's almost 1. So these are different ways that we could move with the same velocity to put us in the path that we want to be in the group. Which one is the best? Which one I should choose? Squared, sine, cosine? How about all of them? If you combine all of them, right, it will give you infinite series. If you do it in this particular way with the coefficient, it will converge to the exponential. So this is the same idea that you have exponential definition of, limit definition of the exponential functions. How many ways you can push this point on that tangent space forward to move along that path? There are many ways, there are infinite ways. How about compound all of them? That will correspond to the exponential function. So first order like this is a one particular choice. If you consider all possible ways you could move using that initial velocity corresponds to the exponential functions, because in the limit, the combination of all of them, the compound of all of them will give you the exponential function. So I think we should stop here. We want to answer the question that how to map the velocity from a specific vector of velocity from one tangent space to another. For that, we cannot do it yet. We need the adjoint map. So next time, we'll talk about the adjoint map. But what I want to do, I want to go through some derivations on handwriting. So take a look at the examples, for example, the cross product, the odometry, so you can make it a little more interesting by doing handwriting.